Hello everyone. In the previous session we have discussed about the electrical circuits and Ohm's law, and in the today's session we are going to discuss the remaining part of this chapter, electricity. First let us discuss about the combination of resistors. In the previous class we had discussed about the simple electrical circuits. Now we are going to see how the resistors are connected in combination and what is the equivalent resistance that we will obtain when they are connected in combination. We are discussing here system of resistors. There are two different combinations possible. The resistors can be connected in series and they can be connected in parallel. The two possible ways of connecting different resistors are series combination of resistors. Next, parallel combination of resistors. Next is parallel combination of resistors. What happens in case of series combination? The resistors are connected end to end. Here the resistors are connected end to end. In case of parallel combination, they are connected in parallel between the 2 points. Here the resistors are connected parallel between the 2 points. Once you see the circuit diagram, you will come to know how the series combination of resistors and parallel combination of resistor look. This is the schematic representation of the electrical circuit when the resistors are connected in series, and this is the representation of the electrical circuit when the resistors are connected in parallel. You can see here the resistors are connected end to end. This is called as series combination of resistors. And in this case, these resistors are connected in parallel between the 2 points. This is called as parallel combination of resistors. In case of resistors in series, the current flowing through each resistor is same, because here there is only single path, so that the current flowing through each resistor is same. It will be I only. Whereas in case of the parallel combination, here there is a junction where the path gets divided. Because of that, the current will also get divided here. If I is the total current flowing through this circuit, once it reaches the junction, it will be divided into I1, I2 and I3. Because these are different paths. Because of that, the current will be divided. This I1 current flow through the R1 resistor, I2 flow through the R2 resistor, I3 flows through the R3 resistor. And again, once the current comes out of this junction, it will be the total current I only. So in case of series combination, each resistor has the same value of current. Whereas in case of parallel combination, the current gets divided. And potential difference in case of resistors in series is not same for all the resistors, as these ends are not connected between the same two terminals. Whereas in case of parallel combination, you can see here all these resistors R1, R2 and R3, they are connected in between the same two terminals. All these three are individually connected to the positive terminal of the battery, and all these three resistors are connected to the negative terminal of the battery individually. Because of that, the voltage across each resistor will be same. Whereas in case of series, the voltage is not same across all the resistors. Now let's see what is the value of equivalent resistance in case of series combination and parallel combination. Equivalent resistance in series combination. Let's draw the circuit diagram first. You should be familiar with drawing the electrical circuit diagrams. It is very important from the examination point of view. These are three resistors which are connected in series of resistance R1, R2, R3. This is ammeter used to measure the electric current. This is plug key. This is battery. of voltage V. This is voltmeter which is connected across these resistors. And we know that the direction of current is shown in such a way that which is opposite to the flow of electrons. That is from higher potential to lower potential. The current I is flowing through the circuit and the potential difference across the battery is V here. Now let's see how the equivalent resistance is in case of series combination. The three resistors R1, R2 and R3 are connected in series. And we know that when the resistors are connected in series, the same current will flow through each resistor because the path of the current is same here. It is not divided. Because of that, the same amount of current, that is I, will flow through each resistor. The current in all the resistors is same. That is I. I is the current which is flowing through this circuit. We know that the potential difference across each resistor is different. How to find out the potential difference across each resistor? By connecting the voltmeter across each resistor, we will get the voltage across each resistor. Then it is found that the total voltage across all these resistors is equal to the sum of individual voltage of each resistor. If V1 is the voltage across R1, V2 is the voltage across R2 and V3 is the voltage across R3. It is found that the total voltage across all these resistors, it is equal to the sum of the individual voltages across each resistor. That is V is equal to V1 plus V2 plus V3. That is the total potential difference is equal to the sum of individual potential, sum of the voltage across each resistor. What does this mean? It means V is equal to V1 plus V2 plus V3. Now we can apply the Ohm's law for finding out the equivalent resistance of this system of resistors. Suppose if these three resistors are replaced by a single resistor such that the same current I is flowing through the circuit and same potential difference is applied across the circuit. In that case, the Ohm's law can be applied for this. In that case, applying Ohm's law to the entire circuit, we get V is equal to IR. And applying Ohm's law to the individual resistors, we get V1 is equal to IR1. Why we have taken here I only? Because we know that the same current will flow through the circuit. Across each resistor, the same current will flow. For V2, we get IR2. For V3, we get IR3. Now, taking I as common here, IR is equal to I into R1 plus R2 plus R3. So, these two will get cancelled. We get the equivalent resistance as the sum of the individual resistance. The equivalent resistance for the series combination of resistors is equal to the sum of individual resistances. So, Rs is equal to R1 plus R2 plus R3. In this way, different resistors can be connected in series and their total resistance or equivalent resistance is equal to the sum of the individual resistances. So, this Rs is called as equivalent equivalent resistance. Let's recall this derivation again. Here the three resistors are connected in series. We know that in case of series combination, the same current will flow through the circuit, and across each resistor we get the same current. And the total potential difference was found to be equal to the sum of voltage across each resistor, that is V1 plus V2 plus V3. And we get, after applying Ohm's law to this equation, applying Ohm's law, we get V. If we replace the system of this resistor by a single resistor such that the same current is flowing through it and same potential difference is applied, then applying Ohm's law to that circuit we get IR. V is equal to IR. And applying Ohm's law to the individual resistors we get V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3. Now I get cancelled on both sides, so that I get the equivalent resistance as the sum of the individual resistances of the three resistors. Now let's see here the equivalent resistance in case of combination of resistors in parallel. Let's draw the electrical circuit diagram first. Now the three resistors of resistances R1, R2, R3 are connected in parallel. Now I is the current flowing through the circuit. But as there are three different paths here, the current will get divided. I1 is the current flowing through the resistor R1, and I2 is the current flowing through the resistor R2. I3 is the current flowing through the resistor R3. The direction of current is shown from higher potential to lower potential. This is the voltmeter connected between the 2 points here, X and Y. This is the parallel combination of resistors. Now we have to find out the equivalent resistance when the resistors are connected in parallel combination. Now you can see here, when they are connected in parallel combination, the different currents will flow through the different resistors. Now how can we measure the current across each resistor? By connecting ammeter in series with different resistors and finding out the amount of current flowing through each resistor. And it was found that the sum of the currents flowing through the different resistors is equal to the total current flowing through the circuit. Understand properly, the total current flowing through the circuit was found to be equal to the sum of the individual currents flowing through each resistor. When three resistors R1, R2 and R3 are connected in parallel across XY, the potential difference across each resistor is same, as individually all these three resistors are connected between the same terminals. The potential difference across each resistor is the same, that is V. Now the total current was found to be the sum of the individual currents flowing through each resistor. The total current in all the resistors is equal to the sum of the individual currents in each resistor. The total current I flowing through all these resistors is equal to the sum of the individual currents flowing through each resistor. So we will get the total current I is equal to I1 plus I2 plus I3. And applying Ohm's law to this equation, we get I is the total current flowing through this circuit. If we replace these three resistors by a single resistor of equivalent resistance Rp, then applying Ohm's law to that circuit, we get I is equal to V upon Rp. It is from Ohm's law. We know that Ohm's law says V is equal to IR, such that I is equal to V upon R. So applying this formula to this equation, we get I1 is equal to V by R1. We know that the voltage is same across each resistor. So we need to take only the V for all the resistors. Then I2 is equal to V upon R2. I3 is equal to V upon R3. So we get, I can write here, V upon Rp is equal to, you can take V as common and get 1 by R1 plus 1 by R2 plus 1 by R3. These two we get cancelled. I get 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So this Rp is the equivalent resistance of the resistors connected in parallel. Equivalent resistance or total resistance of system of resistors in parallel. These two formulae are very important from the examination point of view. You have to remember this derivation and also the formula. Let us solve some questions here. Let me read the question. There are two resistors R1 and R2 having resistance equal to 20 ohm and 30 ohm respectively are connected in parallel in an electric circuit. If the potential difference across the electric circuit is 5 volt, find the electric current flowing through the circuit and the total resistance of resistors. So what we have to find out? We have to find out the electric current flowing through the circuit, and also we have to find out the total resistance. First let us write the given values. The resistance R1, it is equal to 20 ohm. R2 is equal to 30 ohm. And the potential difference V is equal to 5 volt. Now in case of parallel combination of resistance, we can calculate the total resistance from the formula 1 upon Rp is equal to, here there are only two resistors, so we will take 1 upon R1 plus 1 upon R2. Let us substitute the values here. 1 upon 20 plus 1 upon 30. So 1 upon Rp, it is equal to 3 plus 2 divided by 60. This is the LCM. Now solving this, we get 5 by 60. So that 1 by Rp is equal to 5 ones are 5 12s are 1 upon 12. So Rp is equal to 12 ohm. We have calculated the total resistance here. Now we have to find out the electric current flowing through the circuit. From Ohm's law, we know, from Ohm's law, we have I is equal to V upon R. We know the potential difference which is given here, and also we have calculated the total resistance. So from this we can calculate the total current flowing through the circuit. So I is equal to 5 by 12. It comes out to be 0.416 ampere. So the current flowing through the circuit is 0.416 ampere. So we have calculated the resistance. and also the current. Next question. Draw a schematic diagram of a circuit consisting of a battery of 3 cells of 2 volt each, a 5 ohm resistor, an 8 ohm resistor and a 12 ohm resistor and a plug key all connected in series. This is your NCERT question. We should be able to draw the circuit diagram. They have given the 3 resistors are connected in series. And they have also given a battery of 3 cells of 2 volt each is connected. So total voltage will be 2 volt plus 2 volt plus 2 volt is equal to 6 volt. 3 cells are connected. The total voltage will be 6 volt. Now let's draw the resistors. And also they have given plug key is connected in series. This is the current I flowing through the circuit. These 3 resistors are having resistances 5 ohm, 8 ohm, 12 ohm. You have to show the direction of current also. This is the schematic diagram of a circuit consisting of a battery, the 3 resistors and a plug key. All of them are connected in series. So we have studied here the parallel combination of resistors and series combination of resistors. Now the question arises, how do our household circuits are made, whether they are made in parallel combination or in series combination? The answer is they are made in parallel combination. Because you have seen that in case of series combination, when the resistors were connected in series, the same current was flowing through the all the resistors. But in case of household circuit, it cannot be practically possible. We have bulb and also electrical heater. If we connect both of them in series, what happens? Same current will flow through this bulb and heater. But we do not want that. Practically, it is not possible. Bulb requires less amount of current, whereas heater requires more amount of current. But if they are connected in series, what happens? Same amount of current will flow through them. So it is not practically possible to connect the electrical components in series. And also you can observe, if one component fails to operate, the current will not flow through the other component also, because the circuit will become incomplete. Whereas in case of parallel combination, the current which was flowing was divided into different components, so that according to our requirement, the current can be regulated. So it is very convenient to use the parallel combination of electrical components. And also we can observe that the net resistance in case of parallel combination was less than that of the individual resistances. Whereas in case of series combination, the net resistance was more than that of the individual resistances. So how does our household circuits are made? They are made in parallel combination. You have to note this point. Household electric circuits are in parallel combination. It is mainly due to the reason that different electrical components require different currents, and if one component fails to operate, the current will not flow through the circuit. And if one component fails to operate, then the current will not flow through the circuit, because the circuit will become incomplete. If this bulb fails to operate, what happens? The current is not entering into the bulb. If the current is not entering into the bulb, the current will also not be entering into the heater also. So it is not convenient to use these components in series. Through the other components. in case of series combination. So it is often convenient to connect the electrical components in parallel combination, and also the net resistance in parallel combination is low as compared to series. And the main thing is we can individually switch on and switch off the electrical components. The devices can be individually switch on and switch off in case of parallel combination. Suppose the two devices are connected in parallel here. This is the first device. It is connected in parallel with the another device. Switch off this device, then current will not stop flowing through this device. It will flow because the path is different. They two are not connected in series here. So, and if I want to switch off this device, then current can also flow through this device. This is the main benefit of connecting the devices in parallel combination in our household circuits. The next concept of our discussion is heating effect of electric current. We have learned that for electric current to flow in the circuit, an external source of energy must be connected. That is, a cell or a battery is connected. What happens? The chemical action which is taking place in the cell, it is converted into electrical energy. The chemical energy in the cell is converted into electrical energy. And the source must expend its energy in order to maintain the electric current in the circuit. While doing so, some part of the energy, that is source energy, is expended to carry out the work, that is to maintain the current, and rest of the energy is dissipated in the form of heat. The source, which is a cell or a battery, it continuously expends energy in order to maintain the electric current. Continuously expend energy to maintain the current. Some part of energy is spent to carry out the work, and rest of energy is dissipated in the form of heat. Rest of the energy, where is this energy coming from? It is coming from the source, that is a battery or a cell of the source is expelled in the form of heat. And in many electrical gadgets, we require the heat energy, like in iron box, in electrical heaters, we require the heat energy there. So what we do is we will use this heat energy for doing work. How can we do this? We can use the purely resistive circuits for it, where there is more opposition to the flow of electric current. In that case, this energy that is spent by the source is completely converted into heat. For purely resistive circuits, the source energy continuously gets dissipated in the form of heat energy. This is called as heating effect of electric current. When we use the purely resistive circuits, the source energy will continuously expend its energy, which is converted into heat. We make use of that heat in many electrical appliances like iron box, electrical heaters, etc. So understand here that the source continuously expend energy to maintain the current, and some part of this energy is spent to carry out the work, and rest of some energy is expelled in the form of heat. And we can use this heating effect in case of many electrical appliances, and we make use of purely resistive circuits for that purpose, so that the source energy will continuously gets dissipated in the form of heat energy. This is known as heating effect of electric current. Now let's find the mathematical expression for the heat produced in the electrical circuit. Let I be the current flowing through the resistor of resistance R, and T be the time for which charge Q flows through it. Then amount of work done in moving the charge Q through the potential difference V. Then the work done in moving charge Q through potential difference V is given by, we have learnt that V is equal to W by Q. This is the work done in moving this charge through the potential difference V. So W is equal to V into Q. This work done is equal to the energy. As we have learnt in class 9, work is equal to energy. Here we are talking about the heat energy. So let's take here heat H, V into Q. We have learnt that I is equal to Q upon T. So that Q is equal to IT. Substituting this value here, we get H is equal to V into I into T. This is one formula for calculating the heat energy. Again, from the Ohm's law, we know that V is equal to IR. We can substitute this value of IR here. So I get H is equal to IR IT. So this is equal to I square RT. This equation, it is the mathematical form of the Joule's law of heating. It is called as Joule's law of heating. What does this law say? Let's see here. Joule's law of heating says that the heat produced in a resistor is directly proportional to the square of electric current flowing through it. That is, H is directly proportional to square of electric current, and it is directly proportional to the resistance. It is for a given conductor. That is, H is directly proportional to R, and also it is directly proportional to the time for which current flows. Current flows through the resistor. That is, it is directly proportional to T. So We have the Joule's law of heating in the mathematical form as H is equal to I square RT. This is the mathematical form of Joule's law of heating. This law is very important. You have to remember this. The formula is also very important because you get numericals on this formula. So what we have understood here, the heat produced is directly proportional to the square of electric current, which means more the electric current passes through the resistor, more will be the heat produced. And also it is directly proportional to the resistance for a given conductor. More it opposes the flow of electric current, more will be the heat produced, because there will be more collision between the electrons and atoms. Heat produced is mainly due to the collision of these electrons with the atoms. That is, opposition to the flow of these electrons is resistance. More the resistance to the flow of electrons, more will be the heat produced. And also more the time for which electric current flow through this resistor, more will be heat produced. This is all about the Joule's law of heating. Let's see one question here. An heater of resistance 300 ohm is connected to the main supply for 30 minutes. If 10 ampere of current flows through the filament of the heater, then what is the heat produced in the heater? We have to calculate here the amount of heat produced. Let us write the given quantities. First, the heater has resistance 300 ohm. That is R is equal to 300 ohm. And the time for which the current is supplied is equal to 30 minutes. If you convert it in the seconds, we get 30 into 60 is equal to 1800 seconds. Then current I is equal to 10 ampere. We have to find out the amount of heat produced. We know that from Joule's law of heating, H is equal to I square RT. So substituting the values, we get 10 square into 300 into time is 1800 seconds. So it is equal to 18 3s are 54. How many zeros are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 joules. We can also write it as 54 into 10 raised to 6 joules. This is the heat produced in the heater. Now let's see the practical applications of this heating effect of electric current. We know that when electric current flows through a conductor, some part of the energy is converted into heat. Many a times this heat is undesirable. Because of that, some of the electrical appliances like laptop, charger, electrical fans, motors, they become heat, which is undesirable. Whereas in many other appliances where we need heat energy, like electrical ovens, electric heaters, electric toasters, we need heat energy. Let's see some of the practical applications of this heating effect of electric current. The heating effect is used in many electrical appliances like electric heaters, electric ovens, electric toasters, electric kettles, electric laundry iron, which is used in doing work. In all these appliances, most of the energy is converted into heat energy, which is required for doing work here. Practical application of heating effect of electric current is electric bulb. We know that electric bulb is made up of a thin filament. That filament is made up of a metal having high melting point. The nature of the metal should be such that it should be able to withstand high temperature. It should retain heat in it. It should not melt at that temperature when the electric current flows through it. What happens when the electric current will flow through it? The energy is absorbed by the filament. Most of it is converted into heat and some part of the energy is radiated in the form of light. And the material which is used in making the filament of electric bulb is tungsten. It is having a very high melting point of 3380 degrees Celsius. So it will not melt easily. Most of the electrical energy consumed by the filament appears as heat, and some part of it is radiated in the form of light. Electric bulb. The heating effect is used in producing light. The heating effect of electric current is used in producing light radiation. And the filament which is used in the electric bulb is tungsten. The filament used in electric bulb is tungsten, having high melting point of 3380 degrees Celsius. It has the capacity to retain the heat, and when it gets heated it will start glowing, which we receive as heat. It can retain large amount of heat without melting, and it will glow when it gets heated. So here what we are using? We are using here the heating effect of electric current in producing light. What's happening here? The tungsten filament is absorbing the energy in the form of heat, and because of this heating effect it will start glowing, which we receive in the form of light. This is another practical application of heating effect. Another one practical application of heating effect of electric current is making use of fuse in the electrical circuits. What do we mean by fuse? It is an electrical device which protects the electrical circuits and other appliances by stopping the flow of current into them whenever there is overloading of current. Usually fuse is made up of a metal or an alloy having appropriate melting point. When large amount of current more than the specified value passes through this fuse, the wire which is present in the fuse will get melted. So the circuit will be broken and this current will not pass through any appliances and it prevents the short circuits. Electric fuse. What it is? It is device which is used to protect the circuits and other appliances from short circuits. How it is connected with other devices? It is always connected in series with the devices, so that once the metallic wire which is present in the fuse is broken, it is melted, the circuit will be broken and it will not pass through other appliances. The current will not pass through other appliances. It is always connected in series, and it consists of a metallic wire or a wire made up of alloy having the appropriate melting point. It is made up of wire of metal or alloy having low melting point or appropriate melting point. And if more than specified value of current, amount of current flows through the fuse, the temperature of the metallic wire increases and it will get melted. Wire increases and it melts. So this prevents short circuits. This is about the practical application of heating effect of electric current. Now we are going to discuss about the electric power. What do we mean by power? We have learnt it in the class 9. It is the rate of doing work. And in terms of electricity, we define electric power as electric energy consumed per unit time. It is electric energy consumed per unit time in an electric circuit is called electric power. Power is given by rate of doing work. We know that W is equal to V into Q. We have learned it in the beginning of the chapter. So Q by T is nothing but current. V into I. How did we get this? Q upon T is equal to current. We know that current is equal to Q upon T. So we have got here current in place of Q upon T. So P is equal to V into I. This is one formula for calculation of electric power. Again from the Ohm's law we have V is equal to IR. Substituting this value here we get again one more formula for power. So P is equal to IR into I, that is P is equal to I square R. Again substituting I is equal to V by R in this formula. We get P is equal to V into V by R. It is equal to V square by R. So P is equal to V square upon R. This is one more formula for calculating the power. You have to remember all these formulae which is helpful in solving the numericals. And remember here the SI unit of electric power is watt. The SI unit of electric power is watt. When the power is said to be 1 watt, when the power consumed by the electric device, when 1 ampere of current flow through it and the potential difference is 1 volt. The power consumed by the electric device is 1 watt. It carries 1 ampere of current at a potential difference of 1 volt. We have seen here P is equal to VI. P equal to VI. So 1 watt is equal to 1 volt into 1 ampere. So the power consumed is said to be 1 watt when it carries 1 ampere of current when it is operated at a potential difference of 1 volt. Now this unit, that is watt, it is very small. But the electrical energy that we consume is very, very large. So commercial unit of electrical energy is kilowatt hour. We know that electrical energy is equal to power into time. So for power we will use the larger unit, that is kilowatt into hour. For time we will use hour. So that the commercial unit of electrical energy will be kilowatt hour. The commercial unit of electrical energy is kilowatt hour. Is kilowatt hour. It is denoted by small k, big W, small h. Kilowatt hour. How much is kilowatt hour? Let's see. 1 kilowatt hour is equal to 1 kilowatt is equal to 1000 watts. 1 hour is 3600 seconds. So we get 3.6 into 10 raised to 6 watt seconds, or you can also use 3.6 into 10 raised to 6 joules as it is unit of energy. So remember here 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joules. This is all about the electrical power. So with this our chapter electricity is completed. The next session let us solve some important questions including PYQs and also the numericals related to this chapter.